Okay, here we go. Good morning, everybody. Let's get this over here. Okay. Well, we had a nice long weekend, and hopefully you guys are doing well. Um, so let's do some administrative chores here for you guys. Okay. Let's see. What do we have? Let's go to our browser, and let's find our course. So this is Math 262. Okay. And let's see, where are we at? All right. So here we are in the browser. Oh, sorry. I guess I had to turn some things on. I'm not sure what's going on here this morning. So, okay. So here we are in our browser. And let's look for what we have, what I said we're going to do. And of course, you guys have that take-home test portion. And here we are with the take-home test portion. And let's see. Yes, that's the idea, Oscar. We definitely want to make this. This is why it's a take-home portion. Okay. Class time isn't long enough to really test you guys. So the hour, whatever it is, 70 minutes we have isn't really long enough. So that's the whole idea. Okay. That's the point. Anyway, here is what was due. And if you did not turn that in, I don't know what to tell you. Okay. So hopefully you guys got that done, turned in. If you didn't, you still have a few minutes to get it in. So make sure you turn that into the test 2 take-home portion in Canvas and the assignment area. Do that ASAP if you haven't already. That's your deadline, okay? So I said that we were doing this. Probably some people are probably even at this very moment not watching lecture. They're working on it now, believe it or not. But that window is going to close. So that was due already. It's due. So I just want to let people know that. Okay. Also, I did communicate with you guys this weekend. If I go to our online transition here, okay, if you go to the online transition, here's what I actually put. I said I was going to do for you guys as well. So we studied last week improper integrals, and we had the different types with the different cases here. And then you're going to hit examples. And improper integral examples here, like I said, I was going to do for you guys. I uploaded that as well. And I have about I know there's something like 13 pages here. So I have about I think there's 11 or 12 additional examples for you guys. So I highly encourage you guys to also look over these examples. Okay, they're all very, very interesting examples. And of course, they're based on the definition and, of course, evaluating limits. And so I did do that for you guys as well. Okay, so there we go. Just looking through these examples, the work that I did for you guys. And here's some type 2s, infinite discontinuities. So you want to work on those as well. So there's a lot of good examples here about what to do. I encourage you guys to look them over. And this is kind of how we're doing things, right? We get a little bit of lecture for you guys here online, and then you got some examples here as well. So I got those things up. Also, what you guys are going to notice here in Canvas, you do have your grades updated. I also included your grade information this weekend to make sure you guys were all up to date. And so we're actually going to be good to go with that as well. Okay, so we're getting squared away here. And we're going to the new section here today. All right. So just to let you guys know, this is what's going on. We have numerical approximation to integration. So there's a worksheet here, or I should say, here's the notes. And this is what we're going to work with today. All right, so we got these notes, working with this today. Let's get this out of the way here. Okay. And here's your part of your notes that we're going to go with. All right, so this is in the browser portion. We're looking at the notes. And I'm going to go to the iPad now so I can start to get this lecture done. Okay, so make sure I'm going to check really quick on Canvas to see where you guys are at. And what I can check here, looks like we got 35 people turned in what they needed to turn in. So, okay, good. All righty. So again, I know I repeat myself. I'm going to repeat myself again. Remember, we're getting up and running here where you do want to get your cam scanning app up and running. You want to batch scan this stuff. And then you want to upload it to the locations I ask you guys to. The reason I say that is because then I can now grade it in Canvas. If I don't get it in those locations, then I can't grade it. Okay? And if you have any other additional kinds of questions related to that, you guys can come to office hours. If you have trouble getting in, just email me and I'll let you in because it's kind of a little tricky thing sometimes with that Zoom. Okay? All right. Now, we're going to start this lecture here. And in order to do that, we're going to have to go to the iPad. So we got all the administrative stuff out of the way. And here we go. So we're going to go to our iPad now. And what this is going to be, so that people know, this is a numerical approximation to integration. So these are no longer improper integrals. Okay, so let me do a couple of things here. That's not you guys. Let's find the files we need for you. You guys are doing for math 262. So here we go. Here we go. Alrighty, now it should be okay. So what you guys can see here is we're doing numerical approximation to integration. And my function now again here is going to be continuous. So I want to highlight that area here. Say that your function is a continuous function over the interval AB. Okay, so you have a nice continuous function. This is not an improper integral. This is proper, if you want to think of it that way. It's a nice continuous function over a closed bounded interval. So everything's nice. So what we're going to do is investigate here how we numerically approximate when actually we have functions that we can't integrate. And very often, or I should say, everything that you've been seeing, and though you think, wow, this is a hard, question to integrate, and maybe it is to some degree, but, it's just tedious. It just takes some work. It takes some algebra. It takes some background knowledge. However, there's many functions that aren't integrable. In fact, if you try to write down a function arbitrarily, it's not going to be integrable. And that's the problem. In real life, when you want to actually come about answering some questions, you need to have other techniques that can help you integrate. And this is where numerical approximations come in. When you have a function in front of you, you need to integrate, but it's not integrable. And there's a whole area study in mathematics of what that means of non-integrable functions. They're really non-elementary functions. Elementary functions are something that we've been studying for the most part, but there's a lot of functions that we work with that are what's called non-elementary, but I'm not going to go into those details. But here you go. Here's what we're doing. We're going to try to numerically now integrate, and it's going to be over a closed and bounded interval here. Now, what I want to show you here is how we go about this process, because what's important is what you do in the beginning here. And I'm going to change this color. Maybe this is a bit better, yellow. And I'm going to say is that we always start by partitioning our interval. Now, partition means to cut it into smaller segments of equal length. But in order to partition the interval, we're going to partition into what is called n subintervals of equal length delta x. In order to partition, to begin this process, here's what you guys need. We need here this value of n. What is this value? Right? This is n. And n here is really the number of partitions. So you start with this value here, n. How many partitions are you interested in? And after you get this value n here it is, we can compute what's called delta x, the difference. Okay? Those are the equal lengths of our n. Here's our n again. Subintervals. So we have n subintervals of equal length, and the length of each is called delta x. So this is what we want to determine. Okay? So we start with the number of intervals, n, that we're interested in partitioning the AB interval, and we determine delta x. Now, delta x, let's do this here. Delta x, ladies and gentlemen, is found by this formula. So I take the length of the interval from A to B, right? Here's A, here's B. I take that length and I divide by the number of subintervals. That gives me my delta x. Now, this is the important pieces of information we need when we start to partition any subinterval. Okay, and what you guys can see here is that the delta x's that they're talking about are all over here. These are the lengths. So we're looking at how to begin numerical approximations here. Okay? And the first technique is known as the left endpoint approximation. The left endpoint. So when we start the process, of course you say, okay, do I go from A to B? You do. Here's A, here's B. Here's my interval here. We're going to partition this into n subintervals of equal length delta x. So what we're going to have to now do here when we partition is we have these values down here. We have the x0, x1, x2, x3, and that goes all the way to xn minus 3, xn minus 2, xn minus 1, and xn. So we're doing this partition here. And this is where we start. Now, I'll show you an example of what we're talking about. And if I go into the iPad here, the first example I want to look at is the function here. We're going to go from 1 to 2. E to the minus x dx. We're going to numerically approximate this function. And notice it's continuous over the interval 1, 2. So we're going to look at the area under this curve from 1 to 2. Now, I already know we know how to do this. We can integrate this, but we're going to look at how a numerical technique will start. And of course, we're looking for this area under this curve here. Right? So here's the idea. Now, the first step again is always going to be, you're going to use this formula here, right? You're going to use the delta x, that length of the partitions, b minus a over n. N is the number of partitions. Now, when I did this as an example, when I created this worksheet for you guys here that we're going to work with, I started by partitioning n being 5. So we're going to have 5 subintervals. And this is where you start. If we have 5 subintervals, I need to find the length of delta x. Well, I need to know what the values of b and a, the length of the interval, meaning this length, 2 minus 1. So the length of that interval really is 1, and then I'm going to divide by the number of subintervals, which is 5. So in this example, when I start the partition to focus on partitioning, delta x is 1/5, which is also known as 0.2 as a decimal, right? Okay. So here is really how we begin any numerical technique, is we start with the number of subintervals, and we now know the length of each subinterval, called delta x, and it's 0.2. So this is where we start. So I just want to begin by partitioning my interval from 1 to 2, because the interval they're talking about in this problem is 1 to 2. So when you go from 1 to 2 now, let's look at these details. Here's that real number line. You start maybe here at 1, and we're going to start to partition this interval of equal length delta x. So if I say to you guys here, this is your starting point. This is A. This is also known as x naught, your initial point. I'm going to go all the way to B. This is xn. So when we start to partition, and it isn't going to necessarily end there, but I mean, let me show you what I'm talking about. We're going to end at some b value called xn. The next point is going to be x1, x2, x3, x4, and here's x5. Well, I guess it was kind of there. All right, here's b. Now, what's important to always remember is that every one of these distances is of equal length known as delta x. So this is delta x, and maybe we'll color that a different color. Let's get rid of all the red. This is our delta x length. And you guys know what that value is already. That value is 1/5, or it's 0.2. So we're partitioning our interval from 1 to 2 in this example into 5 subintervals. 1, 2, 3, 4, 5 subintervals of equal length known as delta x. This is where we're starting. Now, this is the general idea here, but what are the particular values here, right? What are the values of A and B? So what I'm going to do here is I'm going to go back and I'm going to show you something here. We're going to plug in numbers here. In this example, A is 1. And let's put it right here. And B here is the value 2. So we're starting with this partition. And maybe we should just leave it the way it is like that, right? Let's just do this. We'll call this x naught. And it is the A value. And we're going to say this number here below is 1. This number below is 2. So the question is going to be now, what are these values? x1, x2, x3, x4. So you're going to use the information. You're going to use where you start, where you end, right? All the subintervals here in terms of notation, but you want to remember every length here is going to be, in this example, 0.2, right? So we have to now determine x1, x2, x3, x4. And all you do now, it's very simple. You keep adding delta x. So if I start here at 1, I have to add delta x here. So 1 plus the 0.2 gives us 1.2. Add another delta x of 0.2, 1.4. Add another delta x, 1.6. And another delta x, 1.8. So this is what we're looking for, ladies and gentlemen. This is actually the key to every one of these problems here. Okay, you got to go from 1 to 2. 1, 1.2, 1.4, 1.6, 1.8, and 2.0. Start at x0, x1, x2, x3, x4, and x5. Okay, so these are the key values. Now, let's see if we could go back to our notes on this to look at some of those details. But I'm going to put this in a box because this is important. This is everything to the process. So let's try to box this up if we can. Oops. And there we go. This is our partition. And maybe since we're on the topic here, I want you guys to note something here. What this means is to partition into n subintervals of equal length is I take that original interval, and it's now x0 to x1 here, union x1 to x2, union x4 to x5. And that's continue the process. I guess if we have some space, let's do it. x2, x3. We'll put all of them here if we fit it in. x3 to x4. And then x4 to x5. So here's our partition. This is what they mean of equal length delta x. All right, so what we want to talk about now is the following. And yes, we could describe this as a Riemann sum. In other words, the integral from a to b, f of x dx, becomes the sum f of xi delta x, where I goes from 0 to n minus 1 here. Or we can say, let's keep it at the moment as just for all I. Okay, I'm just going to put an I here. We're going to talk about these details. So here's the idea behind this process. We're going to sum these particular values. So let's look at the details here. Okay, let's go through the details. If I go to my notes here, we have this technique known as the left endpoint. So this is what I mean. Let's leave the eyes out for now. So let me get rid of this stuff that's distracting. Looking at the left endpoint. And I'm going to give you the left endpoint formula here. Okay. So what we want to look at is what this is here. Let's find the highlighter. Ln. We want to look at the definition of Ln. Essentially, what Ln is this. If I look at the first subinterval in my picture here, right? Here's my first subinterval. It starts at x0 to x1. So if you tell me which endpoint in that first subinterval is actually on the left side, So for L, we want to know which point for every subinterval, and your subintervals really look like this in general, xi minus 1 to xi, for all I, which one is on the left? Well, I'm going to help you guys out on this one. What's on the left here is the, let's see if I could keep track of my left and then my right. This is on the left, right? So left, right. So for the first subinterval, x naught is on the left. So I'm going to use that value. So keep that in mind. If I go now to the next subinterval, the second subinterval, I now have to determine what's on the left here. So if I say to you, here's my x1, here's my x2, what's on the left for this subinterval is x1. And in fact, if I repeat the process here and I go to every subinterval, here's the next subinterval. What's on the left is going to be x2. And if I go all the way here to the last subinterval, what's on my left in the last subinterval is xn minus 1. So you guys know. So you're going to have all these values here. This is what you're going to use. So let's write this down here. Well, let's write it down for our case here. The interval here from a to b, fx dx, becomes the sum f of xi delta x, where we say I starts at 0 and it ends at n minus 1. This is what I started to write down earlier, but I wanted to show you where this formula came from. And this here is the left endpoint rule. This is the sum. This is what we're going to sum. This is what we're going to use. Now, I know I'm getting a little bit ahead of myself, but not too much. I guess, yeah. This is in Word, so it doesn't exactly do that nice square thing. All right, so this is what we're looking at. But notice here, we're starting with this I equals 0, and we end at n minus 1 because the left endpoints are in red above here in general. So what I did here is, in our notes here, the left endpoints, this is where we have the rhyme and sum, right? This is where we're adding rectangles. Every one of these rectangles, however, has a length delta x. So if I go here to this general, here's my delta x here. Every one has a delta x. Remember, the length of every one of them is the height of my rectangle. So this is where the f of xi come from in general. So remember, we're trying to find the area here of every rectangle. The height is f of xi. The width is delta x. And if you notice, I place these points here at the left endpoint values. Every one of these points. So x0, x1, x2, xi minus 1, xi, eventually to xn minus 1, they're all left endpoint values. And so here's the derivation, where ln is really I goes to 0 to n minus 1, and f of xi times delta x, remember, that's the area of the rectangle, right? This is finding this area, because my area is the length times the width, or I should say it is f of xi delta x. Sorry, let's get that a little bit better. So we already know this already, and we're going to see this theme over and over again with the remaining part of the course, so I want to go into the detail. So if we do a little bit of algebra here, we know this is a summation, okay? This means to sum. And our index here, I, goes from 0 to n minus 1. So here's what this means by definition here. Okay, notice x naught times delta x plus x1 times delta x plus x2 times delta x, all the way down to the last xn minus 1 times delta x. And what you can do algebraically here is distribute. So you're using the distributive property to get this new formula here. All right, so here's the explanation of where this comes from, this formula I gave you to begin with. And now we're going to see how to use that with a particular example that we're working with here. Okay, so this is called the left endpoint rule. Again, this is ln, and we're going to start by using and computing and approximating the area for every left endpoint here in our subintervals. And we're going to see what this is. So if we go to the iPad again, and let's remember what we're looking at. Here's our function. So if we keep in mind that f here is e to the minus x, here's what we're really trying to do. Numerically approximate from 1 to 2. Sorry. E to the minus x dx. And we're going to use the left endpoint rule. We're starting with L5. Okay, L5. Let's find out what this is. L5, again, we know is defined to be the sum. I goes from 0, f of xi, delta x. So I is going to go from 0 to n minus 1, which is 4. Remember, that's n minus 1. So what I get here will be the summation. I goes from 0 to 4, e to the minus xi, and then delta x is going to be 0.2. So I can start by looking at this way. And, I'm going to go back to the original formula because I think this is helpful for people when they start this process. So if I go to the original formula here, we're going to say, is this f of x naught delta x plus f of x1 delta x plus f of x2 delta x plus f of x3 delta x plus f of x4 delta x. Okay? And you can say, can I factor out the delta x? Sure. F of x naught plus f of x1 plus f of x2 plus f of x3. And like always, oops. Let's get some more space here so you guys can see this. Okay. Okay, here we go. Now, here's what I suggest people do with this process. Right now, you need to determine all of these left endpoint values that we did earlier. Which values are on the left here? These are all left endpoint values. So if you remember which values are on the left, do we have it up here? Here we go. We're going to use these values. This is why we wanted a partition. These are all the left endpoint values for every subinterval. So this is what this means. F of 1 plus f of 1.2 plus f of 1.4 plus f of 1.6 plus f of 1.8, and don't forget to multiply by delta x, which is 0.2. So we plug in all the values. These are all the left endpoint values. So ladies and gentlemen, the very next step that you guys use here is to remember what the function is. You say, my function is right here. It's e to the minus x. So I'm going to plug in e to the minus x here. So this is e to the minus 1 plus e to the minus 2 plus e to the minus 4 plus e to the minus 1.6 plus e to the minus 1.8. And we're going to multiply that by 0.2. Now, this is evaluating the function at the endpoints. So notice what you guys have here. This is essentially arithmetic now. Okay, so this is arithmetic. Now, here's a couple of things that we can do. I can say to you, I do this a couple of ways here. I show people this technique by going to, let's go to, how about this? Microsoft Excel. And what I have in Excel here is the very same question that we're working on. I'm focusing on the left endpoint rule. And what I'm going to do now is I'm going to plug in all those values, meaning I want e. And I think it's exponential. Yeah, exp. Raised to the, or I should say, to the first power here. And so here's all those values that we're looking at. Okay, this is e to the first power. And I believe we forgot something. Let's put a negative there, right? Because isn't it a negative? It is. So that's going to change everything. Here we go. So let's make sure everything is what it should be. It's e to the minus x. Okay. Yeah. All right, so now down here I have the summation here. You say, what's this summation? I'm saying add these values here because that's what that sum is. So ladies and gentlemen, I have this value here for my sum. And I'm going to write that down in my iPad for you for 2.82866. So let's see what this did for us. If we go to the iPad now, I found this sum here. I just have to multiply that sum by 0.2. So if we multiply now by 0.2, we're going to get the approximate area. And I'm going to go to the TI. If you guys don't know, we do have a TI calculator here. And so we can say 1.282866 times 0.2. Here's what we get. 0.2565732. Okay, so here's an answer. I believe here, I want to also show some of you, since you have these calculators, let's actually look at this answer, or how do we do this in a TI, right? Put your parentheses, and now we need the exponential function. So it's second e to the minus 1. Okay, now get out of that power position. Plus second e to the minus 1.2. Get out of the power position. Plus second e to the minus 1.4. Plus second e to the minus 1.6. Plus second e to the minus 1.8. Now get out of the power position again, TI, close that, and then multiply it by 0.2. So you can enter it in a TI numerically as well, or some of the other calculators, and notice the value you get here. So this is going to be 0.2, 5, 6, 5, 7, 3, 5, 7, let's go back, 3, 2, 0, 4, 6. So here's a numerical answer. And notice one is more accurate than the other because Microsoft Excel actually, what did it do? Where's Microsoft Excel, right? Cut off a lot of these values here, okay? It cut off these values to a particular decimal point. So your TI has just a different place that it cuts off. It's a different accuracy. And then I want to remark about this, and let's say to you guys, here's the Excel version. Here's the TI version, and I want you to note the following. That we can integrate e to the minus x dx. That's minus e to the minus x, evaluated from 1 to 2, which is minus e to the minus 2 minus a minus e to the minus 1, which is minus e to the minus 2 plus e to the minus 1, or simply 1 over e minus 1 over e squared. Okay? So let's double check in the TI to see what this could be. And let's go back and delete. All right, let's clear that. So let's do it this way. We have e to the minus 1 minus the e to the minus 2 power. Clear. E to the minus 1. Let's get out of the power position. Minus e to the minus 2. And sure enough, we get 0.2 325441579 as the exact answer. And actually, I should say to you, it's not even exact. It's another approximation. It's 0.2 325441579. That's an even better approximation, by the way. That approximation is more accurate. So notice I'm still using the approximation sign here. This is by integration. If we integrate. And up here, this is Microsoft Excel. This is TI. So notice it's not perfect. This is off. Okay? So these values here are approximate. That's 0.256, 0.256. This is 0.232. It's just approximate. Now, what happens is if you take more iterations, it'll be better, meaning if you have more subintervals, if n is 10, if n is 20, if n is 30, if n is 100, if n is 1,000, then you can have a better approximation. But this is going to be how we compute what's called AL5. Okay, so this is the left endpoint approximation. And now you might say to me, okay, what about for the right endpoint approximation? Right? So what about on the right now? What about R5 or Rn to begin with? Well, Rn here is the sum that I goes from, we're going to have to find the right endpoint values now. We have to find where we start and where we end. Okay, I'm going to say for all I here from the moment. So what about the right endpoints now? Well, for the right endpoint approximation, instead of using for every subinterval, so you go back to the subintervals. Here's my first subinterval. You just have to know your left and your right. Here's the second subinterval. Here's a third subinterval. So for every one of those subintervals, if you could determine your left and your right, here's for the first subinterval, this is my first right value. For the second subinterval, here's my second right. For the third, my third right value. Finally, a right value, and a right value. So notice how we do this. It starts at x1 and it ends at xn for the right endpoint value. So when I say to you guys, take a look, here's a picture, and now I put my point at every right endpoint value. Starts at x1, the next one ends at xn. So we're now going to approximate the area looking at the right endpoint value. So we start at 1 and we end at n in our formula. Okay, start at 1, end at n. So we're going to say here, let's put that here. I goes from 1 to n now. So here's what this means. We have f of x1, delta x. F of x2, delta x. All the way to f of xn, delta x. I can factor out the delta x. We factor that out. And you say, what are the values? Well, what were the right endpoint values now? If we go back, we got to find these right endpoint values. I guess it's not going to be here. Okay, let's go back to notability then. So I'm going to put this in notes. What are the right endpoint values? I guess I have to go all the way back from the beginning here. We started this partition. Here's the partition. Let's get rid of all of this. And the first right endpoint value is 1.2. The second right endpoint value is 1.4, and then 1.6, and then 1.8, and the last one is 2. So I'm going to start at 1.2 and I end at 2. Here we go. 1.2, 1.4, 1.6, and I end at 2. So if you really want to know in particular what this looked like for this example, we can say R5 really is f of x1 plus f of x2 plus f of x3 plus f of x4. So this is 1, 2, 3, 4, another value, delta x. Delta x is 0.2. So here's R5. And we know the function is e to the minus x. So it's e to the minus 1.2 plus e to the minus 1.4 plus e to the minus 1.6 plus e to the minus 1.8 plus e to the minus 2 times 0.2. So what I have to determine again is this sum here, right? What is this value here? Now with right endpoint values. So I can go to, let's go to Excel again. We'll do that. Now we have the right endpoint values here. So I'm going to put exp, that's the function, to the minus 1.2 power. Here's what we get. If I use autofill, I get the rest of the values. Now remember, we need the sums, but let's double check to see if these are okay. That looks okay here. Okay. We need the sums now. And notice my sum is 1.050322. So I'm going to write that down here. 1.050322. And don't forget, we're supposed to multiply that with a 0.2. So if I go back, here's where we're at. We just found this particular sum. Now we have to multiply by 0.2 here, right? This value, that value. And for that, we'll use a TI. So we get 1.050322 times 0.2. Let's double check. 1.050322 times 0.2. And we get about 2.100644. Okay, let's write this down. It's not 2, it's 0. 0.21000644. And this we got from Excel. So if you want to use a calculator, you can. You can say, couldn't I have started with just using the TI directly? Yes, you can. But let's just remember how TIs do that. Second E negative. Now we start with 1.2 this time. Get out of the power position plus second E negative 1.4. Get out of the power position plus second E negative 1.6. Always remember to get out of that power position. Second E to the negative 1.8. And finally, we got second E to the negative 2. And we close this and get out of the power. Oh, go back. We didn't get out of the power position. See that? Get out of the power position. Oh, and we have to go back further. See, not so easy to talk and write at the same time. Second e to the minus 2. Okay. Close that. Okay. All right. Now times the 0.2. Okay. I think we're good. Hopefully we're good. Okay. And notice we get a very similar answer. 2100643731. Very similar answer. And that's from the TI. All right, let's see what this means here. What I showed you guys this morning here is the left endpoint rule and the right endpoint rule. How we go about this. And again, to read about this, or the summary of what we're doing with the right endpoints, everything I did, I proved to you here in the iPad. We did this work. This portion here, this is R5. Notice how we start from 1 and we end at N. So this is the right endpoint rule. And as you guys can see from some of these answers here, they're not so accurate because we only took 5 subintervals. And even for the right endpoint, what you're going to have here is a built-in area or error. And we're going to need to see here how to do better. So here's the question here. Here's what's going to happen now. Here's the big question. Can we do a better approximation The answer is yes. First thing you could do is let n be larger. Get greater and greater subintervals. N is 10, N is 20, N is 100, N is 1,000. You'll get more accurate. That the approximation will converge to the actual area. The smaller the subinterval, right, the greater number of partitions, you get closer and closer to the actual value. You're taking the limit, right? So you're looking at this as n goes to infinity. Because you already have here your definition. If you guys remember this. And we can say, you know, I goes from 1 to n. Doesn't matter. Okay, let n get big. Here's what I'm saying here. So take greater and greater approximate values here. Let n go to infinity. You're going to get, you know, very close. There's another way to do this, though. And you can get better approximations if we actually study additional techniques. So there are additional methods that we can look at. Okay, there are going to be additional ways to get a better approximation, and you're going to see. Now, in this lecture here, in this section, we're also going to study the midpoint rule. So you're going to study MN, and we're going to study Simpson's rule, SN. So we're going to study those two methods. And if you're somebody who says, okay, Mr. Judge, I want to get started on some of those, where can I maybe read some of these things? Well, let's go back here. You can continue with my lecture notes because I'm now showing you here how to do what's called midpoint approximations. And this is where you're going to get what we call MN. And instead of using the left endpoint, the right endpoint, we're now going to use what's called midpoints of every interval. So you're going to take some number in every subinterval. And here's what this looks like. Well, if I can get some space here, maybe look at it down here. Yeah. Every subinterval for all I has a midpoint value in it. And I called it MI here for symbolic reasons, about trying to create this stuff. It was really hard to get these symbols. However, you do have what's known as a midpoint rule, and you're going to see all the midpoints now here looked at. M1, M2, MI minus 1, MI, MN minus 1, MN. They're all midpoints for every subinterval. So you could use the midpoint values. And that'll give you another formula here that I derived. But the key is going to be to partition your interval and find those midpoints. And that's what you're going to want to do. And you could read further. We even have, after that, Simpson's rule, and we'll talk about that. However, we're going to start tomorrow on that midpoint rule. Okay? So I want to remind people here a couple of things here. Let's go back and let's do some things and find where we're at. All right, let's go to the browser now again. So some people may have come in late here. So let's double check and see what we have here. If I look at Canvas here on my phone, yeah, we do have about 39 people turning in that take-home test 2. Good for you guys. That was here. Some of these questions were taken from your book, so you guys know. Okay, and these were the ones that I said, okay, let's see if you could do these here on your own time, and you could, take that time and relax. So they are questions from some of your book, here. They're actually book questions. And also, where else? Okay, yeah, I did post your test 2 solutions as well. That's what I want to remind people. Your test 2 solutions are up here. There are 53 check marks. Look at the small numbers here next to each question. You can double check where your errors are. All right, 2, 3, 5, and so on. That's the distribution. So double check those little numbers add up to the big number. And of course, divided by 53 times 125 is how you got your points. So it's really what proportion times 125. So here is the test solutions for the in-class portion. I uploaded those. And like I promised you guys over the weekend, I gave you additional examples of improper integrals. And there's about 12 or 13 additional examples here. Okay, so those things are there. Those are uploaded for you all. All right, and so I think that keeps us up to date. Yes, and also your grades are in Canvas. So as I input the points for you in Canvas and grade things, which is why I want you to upload to all those places, right? Upload to a particular assignment portion, and I name it completed, blah, blah, blah. So I can use SpeedGrader and grade it, and those grades are automatically entered into the grade book for yourself. And then you can see where you stand. And so sometimes people will ask me, since there's some time for us to go over this, people will say to me, hey, Mr. Judge, I don't know what my grade is. You say, well, why? And my first question to people is, well, why don't you? Right? Why don't you know? It's very simple. You can say, what's my grade? Well, Canvas is nice because it tells you your grade at every particular moment. So if you guys remember, how do you get your grade? It's on the standard scale. Standard scale is 100% to 90% gives you an A. 89% to 80% is a B. 79% to 70% is a C. 69% to 60% is a D. And below 59% is a fantastic. Excuse me. And so Canvas is nice, even though I go by points, but Canvas has this in terms of a percentage. Well, that works for us because I go by the standard scale anyway. So if you said, oh, Mr. Judge, I'm at 82%, well, that means you're getting a B. Oh, I'm at 96%. Well, you're an A. Oh, I'm at 72%. Well, a C. Oh, I got 64%. Well, that means you're at a D. And then if you said, okay, Mr. Judge, I'm at 50%. Well, that means you're getting a fantastic. Okay? So here's how this all works. So that tells you where your grade is at the moment. But also, like I said, I'll be putting in some of those zeros. I'll double check if Canvas even includes blank scores or zero scores. I hope it does. And again, if you guys have any questions or issues, you guys can contact me during office hours. You even have, I even message you guys through Canvas, through comments. When you submit, I send those comments. You could even do some email. You can email me. You can see me in office hours, right? So anyway, that's where we're at. And maybe I should suggest some homework from this section since we're on the topic. This is actually section 8.7. You can get started doing something like 7 to 17 odd, even though that's on Simpson's rule. But we have a few of them to work on, and I'll give you some more additional homework from the book next time so you guys can get started on some of these. Okay, so if you have any questions or issues, contact me during office hours. And like I said, I have been up to date with all my grading. Everything is done except for what you turned in this morning. So if you said, hey, I don't have my test, it's because you didn't turn it into where I asked you to. And I've asked you about 4 or 5 times. And I want you guys to know that, okay? So double check. You should have all your grades up there. If there's an issue, contact me during office hours, and I'll remind you, here's what you were supposed to do, okay? So here's what's going on, and here's where you guys are at. All right, so stay safe, have a good day, and I'll see you guys tomorrow.